All right, welcome back to another episode of Science with Surbeck. Today what we're going to be talking about is light and quantized energy. Now, before we get going into this section of notes, there are a few objectives I'd like you to meet by the end of this video. Objective number 1, compare the wave and particle models of light. Objective number 2, define a quantum of energy and explain how it is related to an energy change of matter. And objective number 3, contrast continuous electromagnetic spectra and atomic emission spectra. So we get into really a review of what we went over last chapter, and that's the basis of the atom. And the atom consisted of protons, neutrons, and electrons, and we knew quite a bit about that nucleus, which consisted of the protons and the neutrons. However, what was really missing was this business about electrons and really where they were in comparison to the atom. We knew they were on the outside, but other than that, there hadn't been much work. And really, this is the next set of questions. This is really the problems that get derived is, hey, where do these electrons, where are they? And so two different branches of science try to tackle this. And so we take a look at the physics side, or physicists here. They said, all right, well, if electrons are around the nucleus or on the outside of the atom, how do they keep from getting pulled in? Because if we would think about this, if we put a plus charged magnet and a minus charged magnet next to one another, they'd be attracted to each other and they would meet together, or they would stick together. Well, again, the physicists are saying, well, how do you prevent that collapse or that attraction from happening where those electrons just don't get sucked into that really strong positive charge of the nucleus? Chemists were also noticing that different chemicals and even different elements had different chemical behavior. And one of the biggest thing that they noticed was that elements that were relatively close together on the periodic table were reacting very, very different comparatively to one another. So chlorine, they found, reacts really, really rapidly. Argon, which is right next to chlorine on the periodic table, element number 18, was unreactive. And potassium, the very next element after argon, was very reactive. So why did we have this pattern? How could we explain it? And what they began to think about was, all right, well, maybe we can think something along the lines of the electrons. And so that's really where the work gets started, is the physicists say, hey, how do we keep this atom from having the electrons collapse into the nucleus? And the chemists say, hey, why do different elements react differently? Okay, so early 1900s, what scientists noticed was this, that when elements got excited or heated up or got energy, they emitted this visible light, okay? And so what they started to notice is, all right, maybe if we understand a little bit about light, we can better understand electrons. So really what they do here, and really the physicists lead the way. There was chemists obviously involved as well, but they try to figure out, okay, if we can understand more about light, we think we can understand more about the electron and the atom. So we really shift our focus here to talking about light and all the aspects that come with light. So in our business about light here, we get this idea that light is just what we can see. Well, that is a very, very small, minute portion. Light, when we consider it in science, we're referring to all things known as electromagnetic radiation. And that's simply energy with wave-like behavior, okay? You can see that our electromagnetic radiation is going to consist of not only the visible light that we can see, but all of these other waves that move through space. So again, broad spectrum, when we refer to light, we want to refer to it as broad spectrum. Okay, we need to first understand, okay, if light moves or has this wave-like behavior, we need to understand the basics of a wave. And so what we get into here is what is being defined as the parts of the wave. So we start out here with the wavelength. And it says it is the shortest distance between equivalence points on a continuous wave. And so it's either going to be measured from your crest to crest or your trough to trough. You can see that wavelength represents one full cycle of a wave moving through a designated point. Now, frequency, on the other hand, is a measure of how many waves can pass a given point in a given time period. Now, typically that time period is 1 second, and that's where we get the International System of Units, or the SI unit for frequency, to be hertz. So it's saying in 1 second how many waves pass through in that given time period. Now, what we also have to think about here is this. Our amplitude, or our height of our wave, is going to affect what values or what we have dealing with, or what we are dealing with in terms of light. And then the last thing that we need to figure out, or we need to determine, is the speed of light. So all electromagnetic radiation, no matter it's visible light, microwave, radio waves, any type of electromagnetic radiation is going to move at the speed of light, and we're going to have the speed of light be 3 times 10 to the 8th meters per second. Now, we can use this to calculate some other quantities that we have discussed up to this point. So that Greek symbol lambda is the symbol for wavelength, and that V is the new symbol, which is the symbol for frequency. So when we want to answer these questions here, we want to know what is the wavelength of a microwave that has a frequency of 3.44 times 10 to the 9th hertz. Well, what we are going to do is we are going to use that formula, C equals wavelength times frequency, and we're just going to fill in the gaps. So on all my problems here, I'm going to put what we know and what we don't know. So we start out with C. C is the speed of light. It will always be given at this quantity, 3.00 times 10 to the 8th meters per second. Our wavelength is something that we do not know. That's actually what the question's asking. So I'm going to put a question mark there. And then our frequency is this. It is given in the problem at 3.44 times 10 to the 9th hertz. So now all we have to do is put this information back into our formula. So we're going to have the speed of light, 3.00 times 10 to the 8th meters per second, equal our wavelength times our frequency, which is given at 3.44 times 10 to the 9th hertz. So now we check out and we want to find, or we want to get, our wavelength by itself. So what we do, we divide on each side. We divide on each side by what is connected to our wavelength. And once we do that, we'll come into our calculation, and we need to consider a couple things. One, we are dealing with numbers in scientific notation. So before I even get out my calculator, I am going to put both items in parentheses. Then what I'm going to do here is this. I am going to take my calculator. I'm going to put that top number in, 3.00 times 10 to the power of 8th, and I'm going to divide it by the bottom number, 3.44 times 10 to the power of 9th. I'm going to press enter, and my wavelength here, my wavelength is going to be 0.0872 meters. So up top, I ran out of room, but our wavelength for this first problem here is going to be 0.0872 meters. Now, what you might also see this expressed in is scientific notation. So if you have a scientific calculator and you still have the answer in, you can hit second, and this button that says DRG, above it says sci to ing. You hit that, you scroll over to science, and you have 8.72 times 10 to the negative second. This is the same answer that we just found. I just want you to know that we might see that in a problem, and I will work through with you how to work that on your calculator. All right, so we want to now, in problem B, we want to find the frequency of a green light that has a wavelength of 4.9 times 10 to the negative 7th meters. So again, what we do, we put C equals wavelength times frequency, and we fill in our gaps. So our C is 3.00 times 10 to the 8th meters per second. It will always be 3.8 or 3 times 10 to the 8th meters per second. Our wavelength is now given at 4.90 times 10 to the negative 7th meters. And our frequency is something we don't know. So we go ahead, we put this back into our problem, and we have 3 times 10 to the 8th meters per second, and that is equal to 4.90 times 10 to the negative 7th meters times that frequency. Again, we want to get that symbol nu by itself, so we're going to divide by whatever's on each side. So we're going to divide 4.90 times 10 to the negative 7th meters, and on our other side, we're going to do the same thing. Now, again, scientific notation, so we need to put a set of parentheses. So we put our set of parentheses, and we turn to our calculator. So our calculator, what we're going to do is we're going to put 3.00 times 10 to the 8th. We're going to divide it by 4.90 times 10 to the negative 7th. Make sure in your calculator you put that set of parentheses. And going out to 3 total digits, we have 6.12 times 10 to the 14th. So this would be 6.12 times 10 to the 14th. And the unit for frequency would be hertz. And that is how we would solve for our two quantities in our wave speed equation. Okay, so we've seen the basics of a wave. Now we need to get specific on that electromagnetic radiation. So the electromagnetic radiation is going to consist of this electromagnetic spectrum, which is going to show all of the radiation. Again, not just what we can see, but all of the radiation. The difference here, and I'll show you this on a chart of the electromagnetic spectrum, what's going to vary is the frequency and the wavelength. As the wavelength gets longer, the frequency will get lower, and as the frequency gets higher and higher, the wavelength will get smaller. Now, the sun that we see obviously contains the visible spectrum, but it also contains all forms of electromagnetic radiation. And we can correlate energy to the size of a wave. So the bigger the wavelength, the smaller the energy. The smaller the wavelength, the larger the energy. And again, I just blow up this chart right here, and you can see all the different types of waves that we have. And the visible spectrum, the stuff that we can see, is a very, very tiny sliver of this entire spectrum. I also want you to notice here that radio waves here are the longest wave, but they have the smallest frequency. Now, if we get over here to gamma rays, which we've already discussed in nuclear chemistry, gamma rays have a very, very short wavelength, but a large frequency. So this is a good page to reference as we answer questions over the electromagnetic spectrum. All right, so now let's get back to that debate or that question that physicists and chemists had of, okay, we just can't explain some of the things about the electron from Rutherford's latest nuclear model that we had. Okay, so what we get here is this. We get this idea of the quantum concept, which we'll talk about here in a second, but it's going to say that, hey, when there's energy and when something gets heated up, like metal, if you put metal, particularly iron, in a hot fire, it heats up and it changes colors. Well, nothing with this wave model, the way light behaves as a wave, could explain that. So now the question is, well, what could? So the scientist here, Max Planck, he says that matter is going to lose or gain energy in these steps or these quanta, and that's that specified amounts of energy. So he says, hey, the reason that there's color is that there is energy being gained on this so-called stair-step line, and he went even further than that. He said, well, I can calculate that, and he did just that. And we'll get to that in a second. But what he said is very substantial in the work to try to figure out how we can connect light and electrons together. So we get to this. Max Planck says, all right, hey, when electromagnetic radiation, when it loses or gains energy, it's going to do so in these stair-step methods or in this quantized form. And all it's saying is, hey, it loses specific amounts or gains specific amounts of energy in this specific form. And again, this was all backed by calculations. Max Planck said, all right, I can calculate that energy of a single quantum by taking his constant, that's that H symbol there, and I'm going to multiply it by the frequency. And he's able to very, very accurately determine the energy that is found in a particular quantum. So again, those stair-step lines had math related to it. All right, the other thing too, so this explains, hey, we put things like iron in a fire and it gets hot and red. We can explain and correlate that to energy. The other thing that was very, very monumental during this time, and it's about the 1930s, what's happening is they're figuring out this idea of the photoelectric effect. And so in the photoelectric effect, they take a beam of light and they shine it on a piece of metal, and one beam of light ejects these particles and another beam of light does not. So they're trying to figure out, well, if light acts as a wave, why does one type of light, a red light, not eject a particle or eject an electron, but another particle does? Okay, so this kind of shocked scientists because they knew that this could happen, and they did experiments and they got results, and they said, well, if light is really acting as a wave, there's no way that this should ever happen. Or we need to figure out there's another piece of light that we're missing, okay? So what Einstein does, and we'll talk about him in a second, he is very substantial, or has substantial evidence to say, all right, that business about Planck, he said that light packs a punch, or light has this designated amount of energy, needs to be combined with that business on the wave model of light. So let's go ahead, let's turn the page here, and let's talk about Einstein in particular. Now, this is just one of something that Einstein was famous for. He took that business there. He knew that wave or that light acted like a wave, but the only way to explain why a electron would be ejected would be to propose that light was dual-natured, and it not only acted like a wave, but it also acted like a particle. And this business came from Max Planck because Planck came up with that energy. That energy is going to be quantized, or it's going to be calculated. So the only way, again, that a light could bounce off a piece of the metal, and it's an electron, so remember, very, very small particle, is that if it packed a punch. So not only does it need to be moving up and down like a wave, but it needs to have some power, so when it hits this metal at a certain frequency, it's going to eject an electron. And again, this is all very, very substantial. This is all very significant items in science. This happened, too, in a very quick period of time when you consider how long some things in science take. So let's get into the specifics, and let's tie it all together here at the end. Again, we're looking at the photoelectric effect, and the other thing that can be done now, because Einstein proposes that light is dual-natured, we can tie that formula that Planck came up with to express this photon. And that photon, remember, is that part or that piece that packs that punch or allows the light to move as a wave, but have that quantized amount of minimum energy. And so we get the formula here. Our energy, E, equals Planck's constant times our frequency. Okay, so in this problem it says, what is the energy of a photon from the violet portion of the rainbow if it has a frequency of 7.23 times 10 to the 14th inverse seconds or hertz? I'm going to make that a note here. Inverse seconds is the same thing as hertz, okay? And so we get to our formula. The formula that we are going to use, I'm going to write it out to the side, is E equals Planck's constant times our frequency. So our E for energy is something that we don't know. Our Planck's constant, a constant, remember, always stays the same, and it's always going to be this value that is written here. And that value will be provided. You don't need to worry about memorizing that particular number there. It will be provided to you, but I'm going to write it down, 6.626 times 10 to the negative 34 joule seconds. And then our frequency is 7.23 times 10 to the 14th. You can put inverse seconds, or more commonly, that frequency is going to be expressed as hertz. So now all we need to do is we need to plug this back into our equation. So we're going to say our E for energy is going to equal 6.626 times 10 to the negative 34th joule seconds times 7.23 times 10 to the 14th hertz. Now, just like we did when we calculated the frequency and wavelength of a particular wave, we're dealing with some large numbers, and they are in scientific notation, so parentheses are key. Okay, so what we need to do here, we're going to put in Planck's constant, so 6.626 times 10 to the negative 34 power. We're going to multiply that by a new set of parentheses, 7.23 times 10 to the 14th power. Close the parentheses, and we're going to press enter. Now we're going to write down three total digits here. So we're going to write down 4.79 times 10 to the negative 19th as our value, and that is the value for E. So we get 4.79 times 10 to the negative 19th 13th, and the unit for energy would be J for joules. And that's how we would go through that process. Now, this second problem is very similar here. It says, what is the energy of a photon that has a frequency of 9.50 times 10 to the 13th hertz? So again, we're going to use the same formula, E equals Planck's constant times our frequency. We don't know what E for energy is. Planck's constant never is going to change. It's always going to be 6.626 times 10 to the negative 34th joule seconds. And then our frequency is going to be 9.5 times 10 to the 13th hertz. And we're going to plug that back into our formula. And so we are going to have E for energy equals 6.626 times 10 to the negative 34 joule seconds times 9.5 times 10 to the 13th hertz. And again, we see that we have scientific notation. Got to have those parentheses. So again, we turn to our calculator. We have 6.626 times 10 to the negative 34 power, close the parentheses, multiply, new set of parentheses, 9.50 times 10 to the 13th power, close the parentheses, press enter, and we get a value here of 6.29 times 10 to the negative 20th joules. So 6.29 times 10 to the negative 20th joules. And now that's saying, okay, we can take a piece of light or electromagnetic radiation and we can calculate that energy associated with it. And this energy can be used to help explain that photoelectric effect. So basically now we have a quantity that can be matched up that a particular piece of light, which acts as a wave and a particle, what energy does it need to knock those electrons off? So this really encompasses, hey, light acts as an energy or as a particle because it has this energy, and a wave, that business that we've talked about previously in this section. So let's wrap it up. We've done a lot of stuff here. We've talked about a lot of things. Let's finish this up. Why is this important for us in chemistry? Well, now we can say this. All right, based on the electromagnetic spectrum, we know that a piece of light, or a piece of light, that's not a good term, light can act as a wave and a particle. What happens is that when we heat or we excite a piece of matter, it is going to gain or lose a certain amount of energy, which we could do those calculations, but it can now be correlated to light. It gives off light. And so with this correlation, we can say, okay, because it gives off light, we now have a basis for what we can explain about the electron. So again, energy or a piece of matter gets excited, gets heated up. It is going to have energy added to it. As it releases that energy, it's going to emit light. And that business about light that we've talked about for the last 25 minutes can be used to help explain that piece of matter. So let's go and let's get to our final page of notes here. And that is specifically talking about that atomic emission spectrum. So here we go. When a piece of matter gets excited, it is going to release energy by emitting light. We just took the time to talk about light, and really we can talk about this as electromagnetic radiation. It's going to release energy. So now that business of light acting as a particle and as a wave can help explain why we need to know that electromagnetic radiation acts as a wave and acts as a particle. We'll see later on, because we know this, we can start to hone in on the details of how an electron acts. All right, I know this has been quite a lengthy video, but there is a lot packed into this section. Again, it's taken and it started off, why do we have this electron? Well, we had to look at the business of light acting as a wave and a particle, and we pieced it all back together. Because matter, when it gets excited or energy is added to it, it's going to release energy in the form of light, and that business that we've talked about with light can help explain why electrons are behaving the way they do. So this serves as our basis for the rest of the chapter in explaining why electrons are so important. I hope you have enjoyed this section of notes in this video. And as always, if you haven't done so already, make sure you subscribe.